2022. This is just going to be a presentation for the broad view of UTAPWeLS. So if you have any questions, let me know any moment. You can also use the chat window if you prefer. That's okay. All right. So first of all, what is UTAPWeLS, right? The very first question. And it stands for the University of Texas at Austin Petrophysical and Well Logging Simulator. That's just where the acronym comes from. Then we just added the 3D because we thought it was, well, because we think that's where we're going in most of the modeling part. And what it does is it's a software that allows you to construct an accurate Earth model. We're going to discuss what we consider the Earth model in a little bit. And making sure that it's petrophysically consistent and in agreement with all measurements. And the goal, the bottom line, is always to have better formation evaluation. That's always what we want to do. And the way we see it, or the way I see it at least, you have the Earth model at the core, which we believe is the true representation of the properties of the formation. You want to make sure that it has this shield, the petrophysical consistent shield, so that everything makes sense and it's actually, you can trust your Earth model. To make sure that you can trust your Earth model, you want to make sure that it's petrophysically consistent. And what we mean by petrophysically consistent is that all properties are consistent with each other using some rock physics models. So it's going to be very much related to the rock physics models that we use, to the petrophysics that we use. And of course, the most important part to make sure that Earth model is actually down to earth is to make sure that the Earth model is connected to any measurement that you may have in that formation. Any log, any core data, any experience that you may have, anything that you know is true should be honored by the Earth model. This is how we see it. Now, what UTAPWeLS is going to do is it's going to help you with figuring out what those properties are, what the Earth model looks like. And we always use the Sudoku analogy. Some of you may have played Sudoku already, and you know how it works. You just have a grid that looks something like this, and they give you some numbers, and you need to fill out the numbers that you don't have following certain rules. You have to infer those missing numbers, and the rules that you will have to follow in Sudoku is that the digits cannot be repeated in a box, in a line, or in a row, or in a column, any line. Similarly, instead of numbers, what we actually have is all the available field data. Like I was saying, all types of logs, all the core data, any field experience you may have. You're going to try to infer that Earth model. Again, what we believe is the true representation of the formation. And you rely on certain rules to do that. Those rules are that all measurements need to be honored and all properties should be petrophysically consistent. So it's like another way of saying the same thing. And again, at the end of the day, what we want to do is we just want to have better formation evaluation. An example of how this workflow can help improve interpretation for formation evaluation. Imagine that you have a resistivity measurement that looks something like this. Doing conventional interpretation, you would say, okay, I have certain property value, certain resistivity value. Then I have a layer here in the middle that has a higher value, and then I go back to the base value. So what you could assume is that, okay, it's just 3 layers that are piecewise consistent, meaning that the property here doesn't really change at all. It's just that here you have a discontinuity where the resistivity goes higher, and then it goes down again. And this is the value that you would assume for the middle layer is just the maximum value that you see in resistivity. Now, if you go with that, you're going to get some result. But if you go a little further and use a simulator with that given a certain Earth model, given these resistivity values, could simulate the tool response, you would see that tool response does not match the log that you actually see. So what you need to do in that case is you have to modify the value for resistivity. In this case, you make it a little higher, just because you see that you're undershooting. And if you run the simulation again, ideally you would see that they match. Now, this value of resistivity is really what you should use for interpretation. And that's what we're saying here, that the resistivity value should be different, and you're going to have better formation evaluation if you use these simulations. Everything around UTAPWeLS is going to be revolving around simulations to make better interpretation. We call the UTAPWeLS interpretation, of course. Now, the Earth model, I briefly described it, but to be very concise about what we mean, because we are well-centered, everything revolves around the well. We have layers that are always around the well trajectory. So we don't have them completely independent. The well trajectory dictates the areas where we are interested in modeling the formation. So we just have the well, and around that well, we have certain layers. The first approximation would be if you have a vertical well, you would just have horizontal layers that are perpendicular to it, and you would have...
Three. 1, 2, 3.
Questions? So it would be just constant properties for, and this would be any property. It could be resistivity, it could be porosity, it could be any property. So you would have the sand porosity and then the shale porosity, this continuously going in this case. Now we have a higher level of description where we take into account invasion. So you would have the well, and around the well you have always completely symmetrical layers of zones of invasion. In most cases, people are used to just having one. You could just have the invaded zone and then the formation zone. If you're a little fancier, you would have first the borehole or the mud, then the invaded zone, and then the formation zone. And we make it so free enough that you can have as many invasion zones as you want. And you may not be doing... Most likely you're not going to do that by hand or something like that. You're going to use some modeling software, and we have a software that simulates invasion, assuming many radial zones. And all properties are piecewise constant, meaning that in any layer or in any radial zone, they're going to be just one value. There's no smooth transitions in UTAPWeLS. They're always discrete. They're always discontinuities. And that goes, like I was saying, that goes whether it's in a layer or in a radial zone. And these two are always assuming vertical wells, and perpendicular layers, but that's not a constraint. The model allows you to have any angle and any dipping for the layers, and it can be changing. So you should be able to use real survey data to have the angles of the well. And then we divide the properties into two types of properties. First, we have physical, which it's a group that has properties that directly correlate to logs, meaning resistivity, gamma ray, those type of properties. And then we have petrophysical properties that are more related to the rocks and the fluids. For example, composition, porosity, water saturation. The boundary between these two is not always clear-cut, but in general, you will know which one you're talking about. And like sometimes one is going to jump to the other group and so on. Depending on the modeling that you're doing, it will be very clear which one is. And even if it's not completely clear in your concept, when you are doing it, you will have a table with one and the other, so it will be very clear. And lastly, we always have the rock physics models that are associated to any layer. The way we handle this in UTAPWeLS is we have something that's called a rock class. That rock class is just a set of rock physics models. So it includes arches or whichever resistivity model you're going to use for that. It includes permeability curves, includes Earth effective medium theory, parameters, and model. It includes many things. We're going to go into a little more detail when we look into that. And we're just saying that there are certain rock classes that always follow those physics. In this example, you could have one rock class for sand and one rock class for shale. In most cases, you're going to have more than that, and it's up to you to decide how refined you need the models to be. but this also allows you to have the model to be as consistent as possible across the different sections of the well and even multiple wells. Any questions or comments so far? Okay. All right. Well, again, if you have any questions, don't be shy. You can jump in. It's okay. All right. Now the software looks something like this. The main window looks something like this. It's where you're gonna have access to your project. You're gonna be able to load, save, so on. There are some user settings that you're gonna access them here, and you can visualize your data, all the logs that you may have, and the well where they belong. And down here we have some quick access data, quick interrogation for any data you may have, main, maximum, and so on. And here you can, it's just either the welcome screen or you can plot the wells along the entire field. They would look something like this. And now each well has a well interpreter associated to it. This is really where you're going to spend most of your time. You can see the tracks. You can plot anything you want, and you can reuse those plots. Here's where you would import data. You would display it. You would modify the Earth model. We're going to look into the Earth model a little more, but this is where you would modify it. You can also modify logs, or you have access to different modules that allow you to modify logs and modify different things. There's certain groups here, Earth model, logs, simulations, inversion, so on. And this is another way of accessing the same submodules. This is how a typical log petrophysical calculator looks like. This module allows you to perform calculations that are preset in logs. I know that in many cases, before you even do interpretation, including layers and assuming piecewise constant values for those layers, before you get into the Earth model, you may want to do some interpretation directly with logs. You can do that here, and we have the equivalent of this, but for Earth model too. Same equations. You just, instead of relying on logs, you rely on the Earth model. We also have a way to perform custom calculations. Any calculation that you can do in MATLAB, you can do it in here. And that, by the way, as you probably already know, but UTAPWeLS is developed in MATLAB. So anything that you can do in MATLAB can be done here. And we're going to talk about scripting in a little bit, but you can access all your data, all your UTAPWeLS data, all your project using MATLAB. And that allows you to have all the power that MATLAB has, including all the statistics toolbox that they have, all the machine learning toolboxes that they have, any software that may have been, any piece of software that may have been written by somebody else, you can use it to apply it to your data. And that's many projects that we have are done doing that. This is just a little access to MATLAB here, just simple equations, but you can do more. We're going to talk about that a little later. You can also modify depth shifting. You can do quality control and make sure that your logs make sense across each other. You can filter logs. Not a lot of people use it, but it can be useful in some cases. We're going to discuss that later. And then the more interesting part, the reason why most of you guys are here, you can do simulations. Simulations, we have many types of simulations. The most commonly used is the resistivity simulation, where given a certain Earth model, which again looks piecewise, and sometimes we refer to it as the blocky log, just because it looks blocky, as obviously. So given a certain blocky log, how would any questions? No, there's no maximum number of wells. You can have as many wells as you want. There might be a problem where if you have too many regarding memory, but I have not reached that point. And I know for us, a big project may have 30 or 40 wells, and I know that for you guys, that may not be all that large. So there might be some issues in some cases. If there's an issue like that, you just let us know and we'll figure it out.
I figured that's where you were getting at when you wanted to talk to me.
Let me. Okay. I'm just muting someone that was talking about something else. All right, get back into here. So there's no limit in wells in principle. If you run into a case where you're having issues because you think you have too many wells, we can look into it. But in principle, there's no problem. So given this Earth model, you can open the simulator, which always is going to give you certain options. You can decide the tool that you're going to simulate. Variant just means who wrote that software. We're going to have many cases where that software was not written by UT. In this case, for example, it's a software that was written by Schlumberger. And in those cases, most companies, well, in those cases, you need to make sure that you have an NDA with that service company. Most people have it with Schlumberger, but not all of them. And so that's just a side note. You just decide the tool you're going to use, the model. There's always going to be some extra parameters here. Some of them are physical, some of them are numerical. And once you say, okay, I want to simulate, you can generate a log that looks something like this. So this is the simulation of this Earth model, and you can see that in some cases the simulation is really not very different from the Earth model, and that's just an example of a case where you really don't need to do any simulation. But you're going to see that there are some cases where the value of or the property that gives you the simulation is really different from that log. And that would be the case if you see a log that looks like this. It would be very hard to just say to just guess the right value for that property. So you need to make sure that you set that right. So this is where UTAPWeLS will be necessary to do good interpretation. Now I have another question. Will the module consider the anisotropy effect to the resistivity due to higher apparent angles? Yeah, no. Here in resistivity, we're gonna have another session, but I will give you all the prelims here. So there is anisotropy. Some tools do consider anisotropy, some do not. So if you are in a case where you know anisotropy is important, you need to there's going to be always a checkbox here that says consider anisotropy, and you just check that box and take it into account. We have two properties for resistivity in that case, or two properties that are going to be necessary. We have resistivity, parallel, and perpendicular. You just need to use both of them to get your simulation going. And the angle, yes, you can set up any angle. If you don't take into account anisotropy, is going to consider the angle, but it's not going to consider perpendicular resistivity. It's just going to consider parallel resistivity. That's how it would work. And then you have to be very careful with the variants. You're going to see 1D and 2D for resistivity. Later, we're going to go into that, but you just have to be very careful, not just in resistivity, but all the simulations have, let's say, reduced geometry that is actually taken into account. Some of them will take into account real 3D model, in which case everything you put into the model is taken into account. But if the model is reduced to a 1D model, you know that certain things are not going to be taken into account. And if it's 1D, it just means that invasion is not considered. And if it's 2D, it just means that the angles are not considered. But we'll get into that with actual examples in later when we go into resistivity. And for simulations, we have resistivity, which is probably the most popular. Nuclear is probably number 2. We have SP simulations, we have sonic simulations, we have NMR simulations, which are a little more complicated. And I know that the entire field has this love-hate relationship with NMR. Some people say that is the best and the only thing you really need. And during this consortium meeting, I was talking to someone that was just saying NMR is just black magic. It's just people believe they're getting something, but it's not. I don't know if it really is. I don't know. I actually don't think so. I disagree in that case. But I know that some people are very skeptical, and we know it's expensive, so you don't always have it. So there's that. But in the past couple of years, we've done a lot of we put a lot of effort in making the NMR module very thorough, and we're not going to be explaining it here during this workshop. But if you are interested, we can always set up another meeting, or we can at least point you in the right direction. But there's a lot of things we can do regarding NMR. Besides simulations, we have also a Sonic Studio. We have an NMR Studio, which is the one I was talking about. In these cases, you go really a lot deeper in the data. For example, in the Sonic Studio, you can simulate not just the logs, but the waveforms. And then you can do STC, the slowness time coherence analysis. And even if you have your own waveforms, you can analyze them there. Some people like doing that for their own data because they get, from the service company, they get an interpretation. And sometimes they want to confirm that interpretation. They want to assume, they want to know exactly what was done and to test different hypotheses. So some people are doing that. And NMR, we have similar things. You can work with decay data. You can work with distributions. You can go back and forth. You can see shoulder bed effects. You can see different possible interpretations. You can even design your own sequence. It's a very, very complete module. We also have another type of simulation, which is the fluid flow. In this case, you wouldn't really simulate a log on itself. You would simulate how deep is the mud going or into the formation, and how all properties change depending on that invasion. And not only that, but you can also do formation testing in this module. I think this is, after resistivity, the second most popular module that people use. And we will go over this one on Wednesday. All right. Now, beyond the simulations that we have, we also have inversion modules, which basically help you do the opposite. Imagine that this log, instead of being a simulated log, this is a field log. The inversion is going to help you recover the Earth model. And it does it by trying to match simulated logs to the field log. We have the most commonly used is MCMC. It's the most general. MCMC stands for Markov Chain Monte Carlo. And we have different methods even in here. And you can use it for any property. We're gonna play with this today. This is the last hour. We're gonna play with this one. And it's regarding inversion, for sure, is the one that is used the most, and I think it's the one that can have the most impact, because it makes, once you start doing simulation, you probably want to do inversion when you're using this in a real case, and this allows you to do inversion really rapidly. So some people use it pretty frequently. Then we have other modules. You can do SP log inversion directly. You can also do resistivity log inversion directly. The difference between MCMC and the other two is that MCMC is stochastic. It's a Monte Carlo method, which by definition is a stochastic. These other two are derivative based. So some people prefer those because the derivatives tend to be more accurate. And they are better. They usually are better at calculating uncertainties, but you can also do that with the Markov chain Monte Carlo. And within the Markov chain Monte Carlo, we have some bias relying on the derivative that can calculate uncertainties pretty accurately. So again, we'll go into this one a little more detail in a little bit, or the following hours. We also have the joint inversion, which is completely different. This one, the SP log, helps you invert for SP logs, resistivity for resistivity logs. The joint inversion helps you do the helps you go from physical properties, so inversions that you do using MCMC, gamma ray, resistivity, density, migration length, and so on, into petrophysical properties. So I think it's the second one that the second most used case, or probably the most useful, I should say, because this allows you to really have very accurate assessment of porosity, water saturation, and at the end of the day, that's hydrocarbon pore volume, which is what we're here for at the end of the day. This is how the Sonic Studio looks like. This is what I was describing. You have the waveforms, you have STC analysis. You can also do it with frequency if you prefer. It's just two different spaces. People that like Sonic use this a lot, or people that work in Sonic use this a lot. And we can also discuss this later if you're interested in it. We don't have time specifically for this one, but if we have enough people interested, we can do another session. Same thing with NMR. You can process the waveforms. You can do frequency dispersion analysis, different ways of visualizing it. And you can also visualize this in the track display, by the way, so that you can compare it with everything else. Then this is for NMR. We don't have time directly in this one, but again, same thing, we can look into it. You can calculate relaxivity given the Earth model properties that you have. You can import NMR data. You can visualize it in 1D or 2D, and you can compare that to previous guidelines that you may have. You can do an inversion, which in this case we mean from decay to distributions. That's what we call inversion in this case. You can run simulations which take into account shoulder bed effects and so on, and you can visualize it in the track set. We also added a couple of tabs this year where allows you to do sensitivity analysis for a set of four properties, and that sensitivity analysis really can help designing sequences, which is something you would do here. You can define a sequence and play with it. It's more into people that are really into NMR, but it can be very useful. This is what people that are not really into NMR but want to incorporate it into their workflow would be using it. And lastly, I'm just going to mention also, we don't have specific time for it, but we have a module for pore level petrophysics. We have not been working on it for a while, but we have it. Some people find it interesting. You can generate, if you have grain densities, we call, how do you call them? Grain size distributions. You can generate a pack, and you can turn that into a voxel image where you can estimate certain properties. Also, if you have CT scan data, you can also turn that into a voxel and get some properties. You can calculate capillary pressure, permeability, conductivity, NMR response. It's low level resolution, and CT scan basically by definition is low level because the size of the sample may not be completely representative, but it might be a good starting point. We also have other features. We have an arbitrary unit system. You can record snapshots. You can. We have a Teglog plugin that allows you to exchange data directly with Teglog. We're also working on. Right now, we only have it for Teglog. During the meeting, you probably remember we had a lot of interest from many companies to have this plugin updated and available in other softwares. So we already have it for, we already started in talks with IP and Petrel. They all rely on the same C++ module called Ocean. So it should be easy to work on that. It should be, before the end of the year, we should be able to have those plugins, because I know that convenience is a very strong force, so we're trying to get them as soon as possible. I have a couple of questions. So yeah, so CT scan has low resolution compared to what? I'm just saying compared to the entire low resolution, meaning the properties that you're going to be able to measure in that core, or that piece of core that you put into the machine is in many cases not representative of the entire formation. That's what I mean. Yeah, probably not the best choice of words, but that's what I mean. And that's what you will see if you play with the pore level petrophysics module. You're going to see that you may have let's say you have core data, and you break it into two different voxels, you will see that one has higher permeability than the other. And they came from the same core. That's just because there's not enough. When you're working with 3D, well, just because it's not representative of the entire core. That's a problem that we have. That's a physical problem. That we also have a numerical problem, which is when you turn this into a 3D voxel, the computers don't have many of these algorithms work in series, which constrains the limit in size drastically, because you have to work with all of them simultaneously. So that constraint may be even stronger when you turn them into a voxel. That's what I mean. Yeah, exactly. So Naomi is responding in the chat, and he's saying that the sample may not be representative. True. To address it, you need multi-scale scaling simulation with subsequent upscaling, and that's absolutely right. That's what you need to do. And that's something we don't have right now, but it would be an interesting project. So if Naum you're interested, or somebody else, we can also talk about that. And then Yemi was asking, can thin sections also be used along with CT scan data? We do have, when you do if you use CT scan, you're just going to get whatever data you have in the CT scan. So thin layers, if they're present, you're going to see them. If they're not present, you will not see them. And yes, properties are going to be measured with direction. So for the same voxel, you will have permeability in each direction. And yeah, so that's possible. If instead of working with CT scan data, you're working with grain size distributions, you are also able to make layers in there. You can deposit first with certain grain size distribution, and then make a different deposit on top of it with another grain size distribution, and so on. Yeah, that is possible. Questions? Okay. All right. So I already talked about the TechLog plugin. We are working on it. We know it's one of the highest priorities. If we want to make sure that people use the software a little more and can integrate it into their everyday, we know we need to get the plugin going, so we're working on that. And lastly,
hi Joaquin, quick question. Instead of just the CT scan data for the imports into the Pore level Petrophysics, could we also work with thin sections or SEM photos? That's actually what I was trying to ask.
Oh, I see. You were asking about 2D images, right? If we can use them to use Pore level Petrophysics, is that right?
Yes.
Yeah. So no, we don't. The short answer is we don't have that in UTAPWeLS. I know there's certain algorithms published that can infer 3D properties from 2D images, but we don't have that. But it's another one of those cases where if there's enough interest from you or from enough sponsors that and we can convince Carlos to get someone to work on them. I think it's a very interesting case because that's the connection between the Pore level Petrophysics and real logs. So that would be very, very interesting, I think. But as of now, we don't have it. That's the short answer. Okay.
Thank you.
Sure. Good. Okay, now going back to scripting, we have, like I was saying, UTAPWeLS is written in MATLAB, and you can access all data from your project from MATLAB. For people that are more inclined to using scripting, this is a very powerful tool. You can write your own scripts, so you can have a workflow and make it very repeatable across wells or across fields. And you can also make extra things, like, for example, plots that we may not have and you want to see three-dimensional plots. You can also use, like I was saying, all the toolboxes that MATLAB has by statistics and machine learning and so on. And anything that you can do in the user interface, anything that you can do clicking around here, you should be able to do in the backend. So for example, you can run a simulation You can do, there's many things. We have many projects that are doing this. We don't have, we have roughly 5 or 6 active projects from sponsors on this. I'm just estimating. And they could be more. Many of them are just sensitivity analysis, given that you have certain conditions. How would the tool behave if you change, water saturation or whatever property? This is a perfect tool for that, because you just make a loop, make many simulations, and you actually see the results. So, and I know this not everyone is interested in doing this, but if you are interested, this is very powerful. So we don't have a specific time similar to NMR. But if you have more questions, or if you want to go over some of it, we can allocate another time, or we can always answer your questions. Okay, and lastly, to get ready for actually using UTAPWeLS, I have a couple of examples that some sponsors have done using the software, and they have presented these results in different consortium meetings. This is actually a student project, but it was Ali Eghbali, you may know him. So this project, he was doing some volumetric composition analysis. So basically using mineralogy for better formation evaluation, and it's a student, but he was doing it for a company. It was like a collaboration, and it's just very easy to do. So I have a question here. With Python, the current range, looking at adding ability to pull Python scripts. No, we don't have that right now. We know it's a constant question. The software was started 20 years ago or so even before I joined the group. And the decision was made, like in many engineering departments, that, well, we're going to be working with MATLAB, because at that time Python wasn't that popular and it wasn't that user friendly. So people were using MATLAB. Many professors were just using MATLAB because MATLAB is just so easy to get in, and it has been very easy to start making short scripts for 20 years or even longer. And then those scripts turned into larger projects, and now we have I don't even know how many lines, but many lines of code that are this giant project. And it would be very nice to turn it into Python. Now it seems like we have a clear winner, or it's been many years since we know that we have I don't know if it's a clear winner. It's for sure it's a lot more popular. MATLAB has other strengths. It's a lot easier to compile. It's a lot easier. There's certain strengths in MATLAB. It's not a completely clear loser, let's say. But for sure, Python is more used broadly, and goes down to the fact that it's free, and now it's very stable. So short answer, we don't have right now any plan, or I don't think we're ever going to have a plan to really transfer everything into Python. What we do have as a plan is to turn the project into a Python package, which MATLAB claims that it's possible, and it has been done. We haven't really taken the time. Many of these projects just take time. And in many of these cases, if you do a very simple function, you can turn it into a package and it works really well and it's fine. But when you have a project, or when you have a package that is already this big, it's not as easy. So this is just to answer Robert's question about Python. Every consortium meeting for the past 2 or 3 years, we've had 2 or 3 sponsors asking for this. So I think next to getting a plugin so that it's easier for people to use it in their everyday work, I think the next one is to turn this into a Python plugin, so that you can do scripting within wherever you use Python, Petrel or whatever. I know that most of these programs have a Python interface, so it would be another way to do it. Yeah, so it's in the works. It's in the works at some point. Also, Naum, how long does a typical resistivity take on a good Windows computer? It also, you have to say a good resistivity simulation. A good resistivity simulation it takes seconds. It's really fast. And my gold standard for good resistivity simulation is one that was developed at UT by one of Carlos's postdoc, which is called semi-analytic, and it's what they say is 1.5 dimensions, which it takes into account dipping and well trajectory, but it does not take into account invasion. That one takes seconds for, I mean, depends on how many data measured depths you're going to have, but you can have hundreds of meters and it's still going to be seconds, even under a second sometimes. Then you have bad cases, or it's not bad cases, but simulations that are really 3D and taking into account more things, that might be minutes. And that might be minutes, yeah. We have also 2D doesn't necessarily mean it's going to be slower. In some cases, 2D is faster than 1D. But that's the typical range. The 2D that we use the most is AIT by Schlumberger, and that one takes for 10 meters, or let's say 20 or 30 meters, takes like 2 seconds, something like that, maybe 3 seconds. So in general, they're pretty fast. Okay, now another project that we had in a collaboration between a company and a student. It was with BP, with Herman Marletti, Michael Rabinovich, and Mohamed Haidi. And from UT, we had Mohamed Benis helping them set up everything. They were studying the effects of reservoir thickness and invasion length on array lateral log response in tight reservoirs. And they just made some, this is what they did. So they had different invasion profiles, and they wanted to see how those look like with the tool response. So it's not intuitive, and you can see how it's different if you have more of a consistent invasion rather than just a piston-like invasion. And they did it for many cases. It was a pretty interesting project that turned out into a couple of publications, and I think in parts that I'm not supposed to know, I don't know, I actually don't know, but I think it was very helpful in the interpretation that they were doing. I don't know the details, which is how it's supposed to work, so that's fine. And then Yemi, he was also using the invasion simulations, but in his case, he was interested in the mud filtrate effects on acoustic logs. So it's a similar project, but completely different goal, and this is just what he was doing. He presented this year, so a couple of weeks ago. And with that, I'm open for more questions or comments. This is typically this is a big open time for questions and comments and interest in where the software is going and interest in what parts of the software you think you're going to use the most. So this is the time to ask questions or make comments. Don't be shy. We don't have a manual for the software. We used to have one, but it's really outdated. It's very old. The problem is that it takes almost as long as to code to do anything. So instead of manual, what we've been doing is we're just uploading videos. I'm hoping that that's enough. For scripting, we have some cases that are available, which is very useful. And we're always open for one-on-one questions. The software, I think one of the strengths of the software is that it's not too big. It's relatively small compared to the other softwares that you're used to using. And I am a strong believer that less is more regarding the design. There's this concept in design and we actually take it very serious when we design the interfaces for UTAPWeLS, where the fewer options you have in front of you, the better choice you're going to make. So we try to make it as simple as possible at first, and then if you go deeper, you're going to see that there's advanced options and then advanced of the advanced, and depending on how familiar you are with the software, you're going to see that it's a lot more complex than it looks at first. But I really think that at first sight, it should be as simple as just click here, and you should get an answer. Now, if you want to refine that answer, you're going to have to go a little deeper. So short answer, there's no manual. Log data does not need to be regularly sampled. It does not. It can have any irregular sampling intervals, and that will work for most cases. There's a couple of places where it's going to be a problem. In the filters, it's a problem, but you rarely use filters anyway. For everything else, it does not need to be regular. The simulation that you perform is going to be regular, so it's going to be compared with, in many cases, when you try to reproduce the field data, you're going to be reproducing it with other sampling rate or a regular sampling rate, but that should not be a problem. Now another question: does the software is capable of handling different tools from different service providers? Yes, we have different tools from different service providers, and is it updated with the recent new technologies of NMRs and EGBs? It is updated regularly. We have some, depending on, this is also a bit of a political question, or business side, not political, but business side, which is not my best side. The more sponsors ask service companies to help us update the tools, the faster this happens. The way Carlos says is the squeaky wheel gets the oil. So the more you insist in getting certain tool updated, the more likely we are to update it. And for example, now that we had enough people asking for the plugin, people from Wintershall are taking the lead, and they're asking not only us, but the providers of the software to allow us to make this plugin. Similarly, Michael Rabinovich is famous for whenever he wants to get a tool, he'll talk to Schlumberger or Halliburton or whomever is responsible for the tool and insist until it happens. So if you have a specific tool that you're very interested, and we're not asking for too much of your time, just send one email saying that you want that one and include the service company. And if we can get more people from more companies, that usually helps get things done faster. But yeah, now going back to the short answer, yes, the software can handle many different service providers. In principle, you're not in principle. In reality, you're not allowed to compare them for business plans. But I don't know. Talk about that with Carlos. So where can I find these videos? We have them in YouTube, and we have them in the webpage for the. Now you're seeing just my browser. So if you just Google UTAPWeLS. Okay. If you Google UTAPWeLS, you're gonna find this webpage, and within this webpage we have some videos, we have some exercises, we have some instructions. So all the material that you're gonna get for this workshop, you could find it here. And we also have the YouTube channel. Most of the videos are here, just because it's easier to get it. So this is where you would find it. Can the software calculate bit-to-bit boundary distance through LWD resistivity? That would be with inversion. I don't think there's a just click here way of doing it, but I'm pretty sure it's possible. Okay. All right. There's more people joining in. If there's any more questions, just write them there. The last thing I want to talk about here is about the installers for UTAPWeLS. Like I was saying, UTAPWeLS is written in MATLAB. There's 3 installers. There's one that is the default, the one that whenever people are just starting, it's the one I recommend. It's called the standalone MCR. If you open the folder, you saw that there were 3. There's one that is SA, which stands for standalone, MCR. MCR stands for MATLAB compiler runtime, which is basically MATLAB without getting MATLAB. So it's everything you need to run MATLAB functions without getting access to writing your own functions. And this is one of the great things about MATLAB. I can compile and send it to you without you needing to have a license for MATLAB. So that's good. If you already have installed the standalone MCR, you can install the standalone no MCR. That just means that it's the same thing without including the MATLAB compiler runtime. The benefit is that it's a little short. It's about half a gigabyte instead of a full gigabyte. The standalone is 1 full gigabyte. So if you care about size, this can be an improvement, and it's a lot faster to install. Probably the most important benefit is that you do not need admin rights to install it. You wouldn't even install it, because the only thing that you need to install is the MCR. So to install the standalone MCR, you're gonna have to contact IT in most cases, or at least have admin rights. This one you do not. So some people prefer this one after they've installed this one. In many cases, there's just little improvements that they ask us to do, little modifications or little bugs they find. So we just make that and send them another version with no MCR. And lastly, we have the MATLAB base. It's just MB stands for that. And to be able to run that one, you must have MATLAB already installed in your computer. We always have a version we recommend. 2021A is the current one, and we update every 2 years or so. So probably next year we're going to update to 2023A. But it used to be a problem. MATLAB was not that MATLAB was stable, but they went through a phase in the late teens of this century, in 16, 17, those years, they were making big changes in the way functions are called. So it was very important to have the right version. Lately, I have not seen that problem at all. So as long as you have MATLAB, you should be able to run it. Now with that, next we're gonna actually get into the software. So was everyone able to install the software? Or anybody, actually I should ask the opposite question. Does anyone still have problems opening the software right now?
You might want to point out another good thing about the MATLAB version is that as far as UTAPWeLS goes, you don't need admin rights to install the MATLAB-based version. All you need is MATLAB. So if you just get that installed, then you can use any of the MATLAB-based versions.
Right. Yeah, thank you, Bruce. That's a very important point, because lately we've been having issues with people with their IT department. It's a lot easier to tell them to install MATLAB than to tell them to install a software they've never seen. So they just get them to install MATLAB and go with it.